Energy cannot be destroyed, energy cannot be created, but it can be transformed to be in another form. So this principle of mechanical energy, principle of mechanical energy, of which we will talk about the first principle, which is called the principle of conservation of mechanical energy. When I say principle of mechanical energy, I'm trying to put an umbrella word for everything. So we're going to start from what we call the principle of conservation of mechanical energy. Okay, then after I will explain what mechanical energy is. The principle of conservation of mechanical energy is examinable. You can be asked that in the exam. The principle of conservation of mechanical energy says that total mechanical energy in the isolated system is conserved or remain constant. It's the same as the principle of conservation of linear momentum. We state that total linear momentum in an isolated system is conserved. So the principle of conservation of mechanical energy is the same as the principle of conservation of momentum. It states that total mechanical energy in an isolated system is conserved. Then we are going to explain what is mechanical energy. Then that will lead us back to talk about the isolated system, because here we are going to focus on energy being transferred to another form. As you know, the principle of energy will say that energy cannot be created and it cannot be destroyed, but it can be transformed into another form. So now, let us talk about mechanical energy. Mechanical energy. What is it that we're talking about when we talk about mechanical energy? Mechanical energy, we're talking about two energies. We're going to talk about two types of energy, which we will focus on in this topic of work energy and power. The first energy of mechanical energy is what we call kinetic energy. Kinetic energy is one of the mechanical energies. Kinetic energy, which we represent by letter EK. We represent by EK. EK stands for kinetic energy. Number two is what we call the gravitational potential energy, which is represented by EP. Gravitational potential energy. Gravitational potential energy. The gravitational potential energy is another type of mechanical energy. So we are going to talk about mechanical energy, which is the gravitational potential energy and the kinetic energy. So mechanical energy is the kinetic energy and the gravitational potential energy. So we write mechanical energy as EMAG, and EMAG, which stands for mechanical energy. And remember that I'm showing you that mechanical energy is two types of energy. That is the gravitational potential energy and the kinetic energy. Kinetic energy is the energy of movement. Gravitational potential energy is the energy which an object has because of its position, because of its height. Gravitational potential energy. Then kinetic energy is the energy that an object has because of its velocity. It's the energy of movement. Then gravitational potential energy is the energy that an object has because of its position to the Earth's surface. I told you that the work done by gravitational force, one can just calculate the gravitational potential energy, and that will be equal to the work done by the gravitational force. Okay, so we use the word Emec to represent the what? Mechanical energy. Mechanical energy is represented by what we write as Emec. Yet mechanical energy is what? Is kinetic energy and the what? And gravitational potential energy. That leads us to represent Emec. Emec, which is mechanical energy, is equals to what? Is equals to mgh plus ek. This is not the formula of anything. I'm just trying to show you what mechanical energy is. Emec stands for mechanical energy. And mechanical energy is two types of energies divided into two, which is gravitational potential energy and kinetic energy. Okay. So actually, let me just indicate to you that the EP, which is the gravitational potential energy, is given by formula mgh. You multiply the mass, gravitational acceleration, and the height of an object. Then EK, we have already spoken about kinetic energy, which is 1/2 mv squared. So these two energies, kinetic energy and the gravitational potential energy, these two energies, they are what? They are what we call mechanical energy. Both of them, it is what we call Emec. Emec consists of gravitational potential energy and what? And kinetic energy. Both of them are called the mechanical energy. I hope you understand what we mean by mechanical energy. Okay. So now let us come back to the principle of conservation of mechanical energy. The principle of conservation of mechanical energy. Principle of conservation of mechanical energy. We are going to focus much on the word conservation. To conserve means to maintain. When we say something is being conserved, it means that thing, it is what is being conserved. So it is being kept constant. What do we mean kept constant? It means it does not change. So the principle of conservation of mechanical energy is concerned with ensuring that mechanical energy remain the same. It remains the same. Okay. Let's say we have an object here. The object is moving from A to B. The object is moving from A to B. The object is moving from A to B on an incline. When we talk about mechanical energy being conserved or conservation of mechanical energy, we mean that the Emec, which is here, as the object it moves, when it gets to point B, it will still be having the same mechanical energy. No amount of energy will have been lost or will have been converted. Remember the principle of energy say energy cannot be destroyed. Meaning that if we have a particular amount of energy here, then when we reach here we have a different amount, we have lesser amount of energy. It will not be because some energy is destroyed, it will be because some of the energy is converted to another form, another type of energy. So the principle of conservation of mechanical energy, it means that the kinetic energy that is here must be equal to the kinetic energy that is here. And the gravitational potential energy that is here must be equal to the gravitational potential energy that is here. So sometimes it's not the case. You find that the energy, as the object moves, energy get lost. and as the object moves, energy gets lost. So we'll be explaining that we are going to talk about conservative force and non-conservative force. The conservative force, these are forces which are going to ensure that mechanical energy is conserved. Non-conservative force, these are forces that are going to ensure that mechanical energy is not conserved, like energy will be lost in some different forms. The principle of conservation of energy. When we say energy is conserved, it means, let's say we're talking about this and now when an object is moving from A to B. What does that mean? It means that, for this one, it means that mechanical energy top is equals to bottom. Bottom. What does it mean? It means that the mechanical energy that is here, it is equal to the mechanical energy that is here. And remember that mechanical energy, we are talking about two things. We are talking about kinetic energy and gravitational potential energy. So when we say conservation of mechanical energy, if we are talking about when an object is moving from A to B, we are saying that we can even remove this top. We can write mechanical energy at A is equals to mechanical energy at B. It means that the kinetic energy and the gravitational potential at A is equal to the kinetic energy and the gravitational potential energy at B. That is the conversation of mechanical energy. Conversation, which means to what? Conservation, not conversation. Conservation, which means to maintain, to ensure that mechanical energy remains constant. It does not change. Meaning, because that energy is not going to be lost, because of the fact that energy is not going to be lost. You know, sometimes when you are speaking these terms, they rhyme, and you find yourself saying some bad English. Although this is not English, this is physics, guys. So, okay, you'll forgive us for sometimes saying conversation. When we want to say conservation, which means to maintain. Okay, so now, let's say I just represented B and A, which I said EMAC top or EMAC B is equals to EMAC bottom, which is A. It means this formula we can further expand it. We can say mechanical energy is what? Gravitational potential energy, and what? And the kinetic energy. So it means that if we are starting from B to A, it means that the 1/2 mv squared, isn't it? At B is the initial, the object is moving from B to A. It means the initial velocity plus mgh and height, initial height. You see initial height, since the object is moving, it will be this height. Understand? Then, when the object is here, what will happen? We're going to have 1/2 mvf. It will be final velocity when it gets here, plus what? mgh, which is f. And this height here, the height will be 0. You can see that the object will not be lifted. It will be on the surface. So this is how we represent the conservation of mechanical energy. We say EMAC top is equal to EMAC bottom, which means mechanical energy at the top is equal to mechanical energy at the bottom. So this is the conservation of mechanical energy. It means that if we happen to use this formula and we get 50 joules here, even here we get 50 joules. If we happen that here we get 50, here we get 30 joules, it means mechanical energy is not conserved. And that will tell us that there are some forces which causes energy to be lost here. The energy with this 50 joules, some of it will be converted in another form. That's why energy will not be conserved. But if here we get 50 and here we get 50, it means energy is conserved. Okay, so now I want us to talk about non-conservative forces. Then we'll talk about the conservative forces. then we'll be moving towards the end of what we are doing. We'll be moving toward the end of what we're doing. Conservative forces. We start by conservative forces. The definition is examinable, right? It's examinable. We say that a force is conservative if the work it does not depend on the path taken. This is one of the definitions. Notice that what we want, we need the work done. Work done. So a force is conservative if the work done by a force does not depend on the path taken. Conservative force is a force at which the work done by that force does not depend on the path taken. You understand? The work done by a conservative force does not depend on the path taken. Then, what about non-conservative forces? Non-conservative forces. A force is non-conservative. A force is non-conservative. A force is non-conservative if the work it does depends on the path taken. You remember that the work done by a frictional force, it will depend on the path taken. You find that we have got the hard surface, a smooth surface. If an object is moving on a smooth surface, it means there is no friction. If it's moving on the rough surface, there is friction. So the path can affect the work done by a frictional force, the path. So, okay, although I'm getting ahead of myself because I've really given you the example of a conservative force and non-conservative force. So these two are examinable. Conservative force, these are forces which cause the mechanical energy to be conserved. Non-conservative force, these are forces that cause the mechanical energy not to be conserved. So when you are defining, you need to include the work done and the path taken, depending on the path taken. So you need to include the work done. So a non-conservative is a force whose work done or the work it does depend on the path that is taken. I will put conservative force and non-conservative force. A force is conservative if the work it does not depend on the path taken. A force is non-conservative if the work it does depends on the path taken. That is conservative and non-conservative forces. Conservative and non-conservative forces. Those are the two important things you need to look at in this topic. You need to know a conservative and the non-conservative forces. Let me give you an example of these forces and I explain what it means, because sometimes they will ask that will mechanical energy be conserved? Why is mechanical energy conserved? So that is based on this information. Let us talk about non-conservative forces. Non-conservative forces. The example of non-conservative force number one, applied force. Applied force is a non-conservative force. The second one is tension. Tension force is a non-conservative force. Number 3 is a frictional force. Frictional force is a what? Is a non-conservative force. These are the 3 forces which we are fond of that we are going to talk about as far as a non-conservative force. So, let's take we have an incline. You see, that is an incline. An object is moving from A to B. There is friction. It's a rough surface. There is friction. Object is moving from A to B. If you hear that there is applied force, and the question asks you that will mechanical energy be conserved, immediately there is one of these forces, mechanical energy cannot be conserved. If there is any one of the above forces, any one of the above forces, then mechanical energy cannot be conserved. You get it, right? If there is any one of these forces, mechanical energy cannot be conserved. If you hear that there is friction, mechanical energy will not be conserved. If there is tension, mechanical energy will not be conserved. If there is applied force, mechanical energy will not be conserved, because these forces, they are non-conservative forces. If you can hear that an object is moving here and there is friction, just know mechanical energy cannot be conserved. What is the reason? An object is moving on a round surface there. Is mechanical energy conserved? No. Mechanical energy is not conserved. Why? Because there is a presence of a non-conservative force. If there is a non-conservative force that is present, it means that mechanical energy will not be conserved. If there is a non-conservative force that is present, it means that there is mechanical energy will not be conserved. What am I saying? I hope you are fine, right? These are the forces. The 3 forces which we call non-conservative force. If they are acting on an object, surely mechanical energy at the top and mechanical energy at the bottom, they will never be equal, because we have a non-conservative force. Then let us talk about conservative force. Conservative force. We're going to talk about the only one conservative force, and that force that we're going to talk about is our conservative force is gravitational force. Gravitational force, which is given by G. Gravitational force is our own non-conservative force. Gravitational force is our own conservative force. So, let's say if it's an object here, it is moving on a smooth surface from A to B. And on this smooth surface, an object it was moving on its own. An object was moving on its own. It was dropped at A. An object was dropped at A. It means that the object is going to move down the incline. The object is going to move down the incline by itself. The object is going to move down the incline by itself. So, as the object moves down the incline by itself, what does that mean? It means that there won't be a frictional force, since the object is moving down the incline by itself. We will not have what? Frictional force, because the object is moving by itself down the incline. This surface is said to be smooth. So it means that there is no applied force, there is no friction. What are the forces that are acting on this object? The forces that are acting on this object is what? It is only gravitational force. And gravitational force is the what? It's a conservative force. This is a force that causes the friction, that causes the energy conserved. So since this is a conservative force, it means that energy is going to be conserved. Since this is a conservative force, it means energy is going to be conserved. So what does that mean? It means that mechanical energy torque is equals to mechanical energy bottom. Understand, right? It means mechanical energy at the top is equals to the mechanical energy at the bottom. Why are we saying mechanical energy at the top and at the bottom are equal? It's because we have got the conservative force acting on an object. There is the conservative force that is acting on an object. It's only one conservative force. If it happens that there was friction, the mechanical energy was not going to be conserved because of friction. You understand? So mechanical energy is conserved because there is only friction that is acting on this object. So that's how we get to explain the conservation of mechanical energy. This was a very short lesson. It's a very short lesson. Then we can start to do the examples and everything. Okay. So I can just explain something just in addition of this. It is coming into my mind. You have seen the conservative forces and the non-conservative forces. If there is friction, there is tension, there is applied force, just know that mechanical energy will not be conserved. If you have that, mechanical energy will not be conserved. Okay. Then now, let us talk about this. Let us talk about the following. You know the conservative forces and the non-conservative. So there is a formula which says work done by non-conservative force. The work done by a non-conservative force, they write WNC. This NC stands for non-conservative force, and I've showed you the non-conservative force, which is applied force, friction, and tension. So the work done by the non-conservative force is equals to change in Emag. What is change in Emag? Remember mechanical energy. You know mechanical energy, which is the gravitational force and the not the gravitational force, the gravitational potential energy and the kinetic energy. So that is mechanical energy. It means that the work done by a non-conservative force is equals to mgHef minus mgHI plus 1/2 mvf square minus 1/2 mvi square. Notice that this is the change in what? This is the change in mechanical energy. Remember, mechanical energy is gravitational potential energy and kinetic energy. So when we talk about the change in those two, we are talking about the what? When we talk about the change in those two, we are talking about mgh and 1/2 mv squared. And the change is going to be final minus initial. So the work done by non-conservative force is this. It means if there is only friction that is acting on an object, it means the work done by friction can be equal to this, depending on how many non-conservative forces are acting on an object. So now we can do the application of this concept. I hope you understand.